All right, so we're just going to do a quick review here of everything that we need to know for this upcoming midterm on Thursday. Okay, this midterm is going to be during class hours. So it'll open up as a quiz. You'll take it and you'll be logged out at the end of the class. All right, so one of the first things that we covered for this new material is SLR assumptions. Okay, so these assumptions, linear and parameters. Okay, so betas are the parameters. So just like y equals mx plus b is the equation of a line, y equals beta 0 plus beta 1x is essentially the same. Okay, so those are, its parameters are linear. Random sampling, okay, so different groups that are being sampled have the same probability of being sampled. Sample variation in x, so basically what we need this to happen, because if we see down here, if x did not change, then x bar, which is the mean of all the x's, would be the same as all these xi's, and so the sum, this would be 0 squared added together a whole bunch of times, and 0 added a bunch of times is just going to be 0, and our denominator can't be 0, right? You can't divide by 0, so that would be mathematically something we couldn't do. So that's important to us. Can't do situations where we don't have variation in x. That shouldn't be too restrictive of an assumption, because it wouldn't really be an interesting situation if we were doing a regression and our x didn't vary. Zero conditional mean. Okay, so in other words, our error term, given that we're controlling for some x, is we're assuming to be 0. Okay, so in other words, our residuals, they're not correlated with x. So there's not something in our error term that's correlated with both our independent variable and our dependent variable. Okay, this is a very commonly failed assumption. Homoscedasticity, so SLR5. So this basically means that our variance is going to be the same given any explanatory variable. So in other words, if I graphed the residuals, okay, so this is at 0. So if I graphed our residuals, what we want to say is that they are random about 0. Okay, that would mean we're good. But if that wasn't the case, oops, wrong thing, let me lasso that away. If that wasn't the case, and I graphed residuals, again, they're mathematically based around 0, but what if the variance increased as x increases? So if this is x, we saw, so it's kind of fanning out or fanning in, or basically it's just different as x changes. Then that would be heteroscedasticity, and that is a problem for us. But luckily for us, in practical terms, all that's really going to do is it's going to bias our standard errors, and there's some fixes for it. I'm not going to go into the fixes, but if I'm running a regression in Stata, if I'm running a regression in Stata, and I'm worried about heteroscedasticity, really we can do this anytime, because doing this will never hurt us, but it could help us. We could say, well, reg, whatever my x variable or y variable is, whatever my x variable or variables are, and we could just say comma, and then after commas in Stata, remember we have options, and our option here could be robust. Okay, and that will give us heteroscedastic, robust standard errors. So it's going to fix that problem. Okay. All right. right, so if the first four are satisfied, then beta 0, beta 1 are unbiased estimators for beta 0, beta 1. Beta 0 hat and beta 1 hat are unbiased estimators for beta 0 and beta 1. I obviously did not put a slash here in my code here, so it actually wrote out beta. So that should just be beta 0. Okay. If all 5 are satisfied, then we can make these statements about the variance of our beta 0 and beta 1. Remember, these are estimates, right? So if we, maybe if we were able to collect a whole bunch of our estimates from different samples, then maybe we'd get some sort of a distribution of them, and we'd have some sort of a mean, and that mean, we could say the best guess of all these different things would be, for some beta j, the best guess would be the average, right? But it could be any of these is what we could actually be calculating. So ideally, we'd like to have some sort of a small variance, right? We'd like to be able to say things about the variance. It's kind of important for that reason. So if all 5 are satisfied, then we can say that our estimator is blue, best linear unbiased estimator. Okay, meaning this particular estimator has the minimum variance and it's unbiased. Okay, so these 5 assumptions are known as the Gauss-Markov assumptions. Okay, now we've got some MLR versions of these. They're very similar for the most part. Linear parameters, that's the same. Okay, so now we might have y equals beta 0 plus beta 1 x1 plus beta 2 x2. So we're going multi-dimensional here, but it's still linear, right? We still got these slope coefficients. We still got this intercept coefficient. Okay, no random sampling again, random sampling again. MLR3, no perfect collinearity. So this is actually really the same thing that we saw here about when we were talking about sample variation in X. But really what we're saying now is that we can't have linear combinations of variables that don't vary. Okay, so what does that mean? So let's say we had male and female, and these are the only groups that we have in our data set. And so you're either male in this data set or you're female, and so you're ones if you are that group and zeros otherwise. So if we added them up, 1, 1, 1, 1, there's no variation here. So we can't do that. So this is the same kind of problem that we ran in with a single linear regression. All right, so we need to make sure that x varies and combinations of x vary. Okay, so in that example, we would just omit one of the variables. So we would omit female or we would omit male. Zero conditional mean, so this is the same, except for now we're saying that our error term needs to be expected to be 0 given all the x's that we're using in our model. Homoscedasticity, so the same as before, but now we're given any value of any of the explanatory variables. We're adding another one here, MLR6. Now, technically, there would be an SLR6 that's the same thing, but we hadn't gotten to that point of talking about what that would mean yet, so we kind of didn't talk about it then. But this is just normality of our error term. It's assuming our error term is normally distributed with a 0 mean and variance of some number sigma squared. Okay, all the implications of the other ones are the same, but now with this new assumption, then we can say, well, the difference between our our estimate and the actual value, which we assume most of the time through our hypothesis testing to be 0, but we could use other numbers. But the difference between these two over the standard error of the beta term is t distributed. Okay, and when it's t distributed, then we can use a t-table and get some information. Okay, in particular, we can do some hypothesis testing with that. So here is some information about that. So these are the 4 different steps that we would take through doing hypothesis testing. Okay, so the first step is to state our hypotheses. So our null hypothesis H0 and our alternative hypothesis H1 or HA, however you want to say it. All right, so exactly what our hypotheses are going to depend on our exact situation, and exactly maybe we know something else. Maybe the thought of what these beta terms should be something other than 0, and we want to test whether or not they are that number. But for the most part, we're just going to say that our null hypothesis is that this coefficient is equal to 0. Okay, it's not letting me erase. There we go. For a two-tailed test, it's really simple. We could just say, well, our alternative is just that beta j is not equal to 0. Okay, and this is what we would kind of draw out as we are making our two-tailed test. Okay, we'll get into what these alpha numbers are to remind you of what those are in a minute. But two-tailed basically just means we've got some space in each side of our distribution. Okay, we'll talk about what that alpha means in a minute. Okay, right-tailed test. So that just means that again, our null hypothesis, we're assuming all our null hypotheses are the same, that beta j equals 0. But now we're saying our alternative would be that beta j is greater than 0. Okay, so that's this one. Left-tailed test, same thing, except for our alternative is that beta j is less than 0. Okay. All right. So next thing we got to do is we got to choose this alpha that I just talked about. Okay, and this alpha is it's our probability of rejecting the null hypothesis when in fact the null hypothesis is true. It's our probability of being wrong in that way. And we're going to use that to determine what's called a t-critical value and rejection region. Okay, so we're told to use the t-table for this. So I have a t-table in this review, so you can download that, look at that. You can use this for the exam. So basically, we would just pick. First of all, am I doing a two-tailed test? Am I doing a one-tailed test? And you, based off of which one you do, you choose your alpha. Okay, so if I was doing an alpha of 5% and I was doing a two-tailed test, okay, then I would want to use this column. And then I would look at degrees of freedom. And degrees of freedom are just our number of observations in minus k, which is our number of x variables. Okay, so a number of independent variables, minus 1. And the reason we're subtracting 1 is, again, we're subtracting from in the total number of statistics that we're creating simultaneously, which would be the number of regressors we have plus the coefficient, the intercept, right? So we're creating the intercept, beta 0 at the same time. So we have to take that into account. Okay, so let's say that we have 40 observations, and let's say we have 3 x variables. Okay, so our degrees of freedom would be 40 minus 3 minus 1, or 36. Okay, so we go down here and we see, well, there's a 35. So I'm not going to make you guys find the exact number. I think 35 would be close enough for us. Okay, so we find that number and we go to the right column. So this is the right column, and we would see 2.03 is our number. So this is our t critical value that we are looking for. And once we find that value, we're going to put it in our graph that we're going to make here. Okay, so let's say this is 2.0. I can't remember what it was. Let's say 2.03. Okay, for a two-tailed test, we would just replicate that on the other side by saying negative 2.03. But if I was doing something else, if I got that same number, let's say for right-tailed test, which we probably wouldn't, right? We most certainly wouldn't. But let's just say we did. So 2.03 and negative 2.03. Okay, so this is not the way to do it, but we're just giving some numbers for some examples here. So basically what this is saying, what this first one is saying, is that there's alpha over 2, or 2.5% alpha of the probability space is to the right, of this 2.03. And same thing here, there's 2.5% of the probability space to the left of negative 2.03. Okay, and again, if I happen to get this number 2.03 for this right-tailed test, which again we wouldn't with the same number of with the same alpha and the same number of observations, because we kind of half the probability space in each side here for the two-tailed test. So we wouldn't get the same number, but let's just assume we got this number 2.03. This is just saying for right-tailed test that to the right of 2.03 that there's 5% of probability space. So this area right here going on to infinity in this direction is 5%. And again, for the left-tailed test, if we happen to get this number, negative 2.83, then we're saying that anything to the left of negative 0.03, this is 5% of the probability space. Okay, and this probability space, we're saying is given this number that we chose, alpha, we're saying that's far enough away from 0, our null hypothesis, which is going to be right here. We're saying that's far and away enough from 0, such that we are willing to accept being wrong if we reject HO when it's actually true. Okay, so if we, in this next step, we compute this t statistic, and it falls within this region, either here or here or here or here. If it falls within that region, then we can reject our hypothesis. So what is this t statistic? Well, it's just beta j hat, which we should be given most of the time, over this says beta 2 hat, but that should just be beta j hat. So over its standard error. Okay, so if I find that number and that number is within these rejection region that I drew, then I can reject. Okay, or I can fail to reject. Okay, so if it's within the rejection region, we would say we have evidence to reject the null hypothesis, and if we can't reject, if it's not within the rejection region, it doesn't mean that there isn't some effect, but it means that we fail to reject. We don't have enough evidence to reject at that point.